All right, that's good. So we were talking about conjugate functions. Anybody remember what that was? So given a function f of x, what was the definition of a conjugate function? Okay, so x belongs to okay, and f is defined from all right. So what all did we see in terms of its properties? Did we say something interesting? Very important. Whatever f of x be, f star is always convex. And what's the two-word answer or justification? Is always convex. It's a sorry.
Max of linear appendix.
That we have proven to be convex. This is always convex, irrespective of f being convex. What else did we do? We computed f star of y for some particular choices of f. Which are them? For some f of x. So which are the nice ones? There's one of them. And what did it turn out to be? Something is very interesting. So if I were to take one more star, I would get back x square. So in this particular case, what we see is f star star is actually f. So this is actually true as long as f is convex and its epigraph is closed. We'll prove this. So I was just making the homework number 3. It will be, but it's also sketched out how to prove this. There are many ways in which you can do this. One is looking at the supporting hyperplane at a particular point on the epigraph. Any other function did we care about?
We'll give an example function why it is not true.
What is not true? Okay, that's good. So it's not in general, it's not true. It's very important to also construct one such example. And what was that? Log of x? Minus log of x.
That will convex is.
So let's first try to compute what is f star of y. Sorry? This will be minus of log of y minus 1 for what domain?
Or it's greater.
I'm not talking about f of x, but you can compute this is straightforward.
How log of negative is not negative.
Sorry?
So log of negative is not negative.
Okay, so what should I do?
0 to log of minus y.
What should I do instead of this?
0 is greater than.
Y is greater than 0.
Between 0 and 1.
Y is 0 and 1. Okay, consensus. Just think about what is the right fix. There's only one right fix. Look at the definition. What will the definition look like? Soup over y transpose x plus log of x. And what is soup over? Minus log of x has to be. Okay, so what is the answer here?
So that term was always it will positive. Or not positive because the first.
What kind of function is this? Y transpose x plus log x. For example, for y greater than 0, what kind of function is this? It just keeps going on. So that's one of the cases you should consider. How can you yield it back? What value of y will control that function? Negative y, okay. It's so suppose y is negative. What is the optimizer? So clearly domain of f star is
I will be optimized on y equals to x, right?
y equal to x or 1 by x or whatever. They're getting multiplied here, right? So
It's really good. More norm of x square.
where is norm? Where is norm here? Anywhere? So is this point clear? Otherwise, it just runs off to infinity. Okay. So now under this, what is the optimizing x? What kind of function is x transpose y plus log x? What is the guess, even if you did not know differentiation? What's the guess for optimizing x? Can somebody draw this function? Yx plus log x, where y is less than 0. Let's pick y equal to -1. What kind of function is this? Minus x plus log x. What does it look like?
It should.
What?
So for x plus log x, it is like a
Minus x plus log x. Log x is like this. What does minus x look like? Here?
No, this 135.
135 here.
Negative part. Negative part. Right?
This one?
Yes. Yeah.
Okay. Okay, so that is minus x. This is log x. You add them together, what will happen? What kind of function is minus x plus log x?
It's going increasing there.
Yeah, but we're trying to find a maxima of this, right? So what is sufficient to, what is x? Convex, concave? Both. So is minus x. Okay. So minus x plus log x is what kind of function?
So in B2,
If you add two concave or convex functions, what happens? So minus x plus log x is what kind of function? So if I'm trying to maximize, what should I do?
basically, we're going to figure out both of the lines again.
Yeah. So if I'm maximizing this function, what value of x will work?
That's one.
Okay. So now tell me in general for what y it will work. Now y is some number less than 0. All that I've done is this.
That's minus. It's not that.
It's straightforward. So x star, nothing but and what is the answer we get?
Minus.
All I need to do is to plug it here. So log of minus 1 by y. This is simply minus 1. Log with the inside minus will just come out and you'll end up getting all that you need to do is just minus 1. Hopefully I'm doing that. Yeah. So now here you get to see that the conjugate will not come back to log x.
The other constant part.
All right. So let's do one more. Oh, so now let's take f of x, the norm of x. Okay. What will be its conjugate? Yeah.
Everyone, like every X,
Mhm.
the same value. It's linear.
But what is that value? You're partially correct. It will not depend on x, but will depend on y. What is the conjugate function? F star of y.
Normal that will be the square root of right transfer. That would be the chain rule and one by two, and then 2x. We're taking the derivative. Right? We're taking the derivative.
Do what you want. But this is somewhat special. That's why I wanted to bring this out. The answer will not depend on x. I'll take only two values essentially. To pick a value of y, try to tell me what's going on. So suppose y is very large. What happens?
Or x greater than 0. In
Why x greater than 0? Norm is defined, well defined for any x, right? What is the problem?
X equal to 0, the value becomes 0.
Fine.
Yeah, that places if we take x equal to y, then the value will be norm of y square minus norm of y.
But that could be strange. That's strange business. Go on. So can you try to characterize it in terms of the dual norm and defining it for the first time? Okay. So you can take this as a definition. There can be many other names to this. So a dual norm of z, I'm going to write it as z star, is supreme over, we call it w star z. That's the dual norm of z. What is doing? It's taking an inner product and supremizing over all w with unit norm. Can you give me a geometric interpretation of this? What does it mean? So pick your choicest z. Let's work on, let's say, R2. Tell me what, for a special z, what will it look like?
So if you get z also from the unit norm, so it is like a dot product of two vectors. The inner product of two vectors
Yeah.
on the unit norm, and it is and the inner product is maximized when the linear frequency. One of them is scaling of the other.
Yes.
So the supremum should attain when W is the normalized Z, like Z by norm.
Z by norm of z. Correct. Okay. So now, in terms of norm of y, can you characterize this answer? The norm is the star norm. So take two cases, y star to be less than 1. Yeah. What will happen in these two cases? When y star is less than equal to 1, what relationship do you get for these two terms together? Y transpose x minus mod x.
That is equal to norm of Y star. Like Y transpose X minus norm X is
How much?
norm of Y transpose X minus norm X is less equals to norm of Y transpose X, and from that supremum in that inequality we can tell that is bounded below a dual norm of Y.
Okay. What are you trying to say eventually? Are you giving an upper bound on this in terms of
Y.
a number or y? I'm given this,
Norm of Y.
which is at most 1. So you're saying in this case, y transpose x minus mod x is less than 1 for all y. Is that what you're saying?
It's the norm of.
It's given.
Yes.
There's nothing about if anymore. What does this definition tell us? When the star norm of y is less than 1, what does it mean? That the supremum over all possible. What? Sorry? That is given to you. Now, what can you bound f star of y by? That's all I'm asking. What I've written on the board to the left of that is incorrect. Apply the definition of the norm and tell me an upper bound of y transpose x in terms of norm of x. Why is this so difficult? By this definition, what does it mean? That y transpose x is less than or equal to by this definition. This one is 0.
One.
This one is how much?
Like when norm of vector is less than or equal to 1, then the supremum of the x star of y is 0.
Don't go there directly. What is an upper bound on this?
So
When y star is less than 1, what is an upper bound on this quantity?
0.
Why?
You can take the inner products of y and x. Norm of y, norm of x, cos theta.
Why are you going to so far? Is it needed? All I have given is that y star norm is less than or equal to 1. How does that imply that?
Okay, so if you have y star of norm is equals to 1, then y transpose x is less equals to norm x.
Why?
Because of the
Give me a one line argument. That's all is needed.
yes, if you just put instead of z equals to x and omega equals to y.
Tell me what are you doing?
Z equals to x and omega equals to y.
Omega w.
W equals to y.
Okay, so x star is equal to supremum w is y transpose x. Yes. Now
So the maximum norm of if for any vector x, for any vector y, the maximum norm of y transpose x is bounded by the dual norm of x star.
Yes, that is what is, this is true.
Yes.
Okay, now.
So
Why
I'm
do-
taking an upper bound on y transpose x
Mhm.
by dual norm of x.
But where is this appearing? That's the condition I'm given, right? That the dual norm of y is at most 1.
Yeah, but we can take also the dual norm. We can take the instead of regular norm, we can take the dual norm of y star.
Where? Here.
Yes.
That's not my definition. If you want to do something, you have to tell me why it is justified. Here, what is the definition? This is the usual norm.
Yes.
This is the new norm.
Yes.
Your answer is not wrong.
So doesn't that y norm of y star less than equals to 1 imply norm of y less than equals to 1?
Norm of y. Why?
Okay, so by similar argument, I think we can show that that dual of dual norm is the same norm that we are
I
wanting.
don't complicate matters.
So what is that? If we take W trans W is equal to norm of y by norm of y, then
Let me just
one of the values.
carry on.
If we take W is equal to y by norm of y.
Which norm? This norm?
Yes, the
Okay.
then we know that norm y star is less than greater than equal to substituting this y in the that you get.
This W.
Yes.
Okay. So I'll get y transpose y
Right.
over. Okay. And this is at most 1. Okay. So why does it help me? Even if this is true?
Then
What do I want? I want this. This is what I want.
Y transpose x is less than equals to norm of y into norm of x.
How do I know that? It's true, but how do I know that? Something in the world called Cauchy-Schwarz. What does it imply? You're right. Just say it.
Expectation of
Why expectation? There's no expectation required for Cauchy-Schwarz. It's precisely what you're asking for. It's exactly that.
0.
With 0,
Supreme.
where we jump into the answer? There is one step in between required. You will show that this is less than or equal to 0, then it is just obvious that the supremum is 0. And he has essentially finished. I don't know why is it taking so long.
Norm of xy is less than equals to norm of x into norm of y.
Why are you complicating? You said the right thing.
Right.
Is this not true?
Yes.
And what have you shown here? So, what does it imply? That exactly is what it is. Don't hesitate. If once you get to the right answer, just go for it. Worst case, what will happen? It may not be correct, but at least if you're on the right path, keep going. This is in fact 0 as long as y star is less than 1. Now, what happens when y star is greater than 1? So this is also an interesting inequality to keep in mind. The usual norm and the star norm have a relationship between them. What does it even mean? That there exists something, something. What is that something, something? For which its own norm is less than 1, but W transport Y is greater than 1. In particular, sorry,
That is this norm of y is greater than 1.
norm of Y. What do I need? Look at the expression what I need. Again, I need Y transpose X. Something to say about Y transpose X. So when Y star is greater than 1, there exists a W such that W with less than equal to 1, such that I just want to make sure W transpose Y is greater than. That's all I'm giving. The quantity of interest is Y transpose. The transposes are okay, you can always keep changing. This is what the quantity of interest is.
We take the norm of x common outside, then
Here?
Yeah.
Okay.
we can write it out. But this quantity is well,
There exists a particular X for which at least I know that X transpose Y is greater than 1. Okay. Carry on.
maximum of the supreme of it will be the norm of y star minus half. It's close to infinity.
Why? Why does it do that? All I haven't.
W for its y transpose W by norm of W against this norm y star which is greater than 1. So subtracting 1 we still get a positive quantity.
Mhm.
And since x is no longer the norm of x if we keep increasing the norm of x, then the quantity will.
Can you give the punchline? Somehow you're saying that the thing in the bracket is non-negative or greater than zero.
Minimum is not.
Yeah, but you can't take separate supremums, right? Either you tell me that there exists an x or exists exists an x for which somehow this overall thing is growing. That's what you have to show me.
So we can take any r times w.
Okay. R is less than 1?
No, any r, real r.
Yeah.
Real r.
Okay, so R greater than 0.
So if we take x equal to r times w,
X equal to R times W.
then this will get
R times
norm of w will be 1.
less than 1. Okay.
Times this will be y star, norm of y star minus 1.
Even with the denominator.
This is r times w, then this will be w by.
So this is simply R times W, right? And what is this? Y transpose? R times W. Okay. So
R and w will be cancelled.
R and R goes, but what is this? That's not the same thing, right?
The only point is if the y star is greater than or equal to the previous one.
So if it goes over here, what happens? Norm of W is less than equal to 1. While Y transpose W is, am I not done? I don't necessarily have to cancel this off. So if you look at this, this is R times W, Y transpose W minus norm of W, whole divided by norm of W. This cancels off. This is less than equal to 1, but this is greater than equal to 1. So this whole quantity is greater than 1 time, not 1 time, some positive number times R. No, let's call it some A for some A. So now what is R? R is allowed a free variable. So if this is true, supremizing over R will only give you infinity. Is everybody okay? What happened? All I was given was this for all W's less than equal to 1. So just planted X equal to R times W. And the end result is some A times R, where A is some fixed quantity, R is under my control. Yeah. So it's a very interesting function. So what it ends up giving you is that f star of y is 0 in this case and infinity in this case. This takes two values. Some basic properties. This is really the reason you're calling them conjugate pairs. So you look at f of x and plus f star of y, making sure that you can actually add this, not writing in great detail. All of this should be well defined. What should this be? Is there some interesting inequality you can write just by our definition? Remember our definition. What is the definition? F star of y is sup over x, y transpose x minus f.
Y transpose greater than.
Is greater than?
Right.
Does it remind you of anything?
That's fine.
Sorry?
The same. It's there in the assignment.
No, not the same. Something you've seen before this class.
F of y was greater than equals to f of x plus the gradient of f times y.
That was for convex functions. Here I have not invoked anything. So f need not be convex. I'm pretty sure you've seen this. So what happens when f is differentiable? What does this inequality take shape? Let's do that. Let's suppose f is differentiable. What will happen here? Let's compute f star of y when f is differentiable. And let the domain of f be all of Rn. You don't have to worry about. So that
Differentiate.
yes.
We
So
can get the optimum.
what will that be?
F dash x by y.
That's what I'll get if I differentiate with respect to x. What does this mean? If you remember the picture I drew, I have to make sure that f is differentiable. Right? That's roughly my picture was. And let's say this is my this line, which is what is magically something happens. Okay, so this is my sum. What is that line I'm drawing? Which is somehow shifted. I can't erase it. This is a y transpose x line for a fixed y. Right? Now, what was my f star of y for a particular something like this? I don't like. So now the fact that this relationship holds for a differentiable y, a differentiable f, what does it mean in terms of this picture? Let me try to see if I can move this around. You can actually move. Yeah. Let's keep it over here and let me try it again. That's my y transpose x. And this is my function. Okay. This is what f star of y was. Now, given that y star is equal to del f x star, I'm just putting a star to know that they're special, that optimizing x star satisfies this relationship. If you don't like y star, let me remove y star. So, any interpretation from our picture? What is going on?
It is just not observing how the distance, the length vector is changing along.
Does anything strike? What is this distance? Isn't it the same distance as here? Okay, so the optimizing point X satisfies this relationship for a fixed Y. What does it mean in this terms of this picture? Or equivalently, you can plant it back and try to see what does F star of Y look like. So once I put it back, what will I get? Y transpose, so that is del Fx transpose X minus, that's your F star of Y. You can flip it around if you don't like gradient transpose multiplied by X. X transpose gradient is the fine. Now, is there an interpretation of what is F star of Y in terms of X times the gradient minus F of X? If you don't like this nasty function, you can think of any nicer function. Let's say X square.
The slope of the slope of y transpose X in that case will just be the gradient of F of X. Is what,
Say it again.
as in we found that y is equal to the gradient of X.
Yeah.
So the slope of the line y transpose X is the gradient. Because y equal to m X plus, but we can see the m and m is the gradient of F.
Y is gradient of F. That much I understand. When you start multiplying the gradient with X,
So that line.
yeah.
F of X equal to y transpose, like g of X equal to y transpose, it's that line
Mhm.
is has slope gradient of it.
Fine.
So that line is parallel to the tangent of uh, tangent of the curve at x where at
Yeah.
this value of x.
Yeah.
So then
So drawn something, right? Can you use that picture and tell me what exactly I'm doing?
that is the maximum distance between the line and the.
No, in terms of what I've written there. That F star of Y is gradient times X minus F of X. So where is the gradient times X?
That is that line.
Which one?
The upper.
Okay.
And,
Go on.
yes, so f of
All
x.
I'm doing is just shifting it by F of X. So if you look at F star of Y, what have I done? As he's saying, this is a Y transpose X line. When Y is gradient, this is exactly parallel to that. So this is the line which is taking care of the first term. And how much is the shift? The shift is by minus F of X. So exactly this distance is nothing but F star of Y. No, not happy. Everyone happy? Not happy? Please, this is the time to express your unhappiness. See, it's written in terms of x's, but x's, you can flip it around and find the y. So always keep in mind, the way I'm writing in terms of x. That makes no sense, right? Because it's a function of y. But always keep thinking that y is nothing but gradient of. So there are many ways in which you can write this. This is the easiest in terms of x. So you look at the slope, add the point x, and then take the line passing through the origin, then shift it down by the value of f of x. And x is a special x for which this is true. So you are given a particular y. For that particular y, there exists an x star for which I am evaluating this. Okay. Let's see what happens. So let's say f of u comma v is separable. Let's call it f1 of u plus f2 of v. What can you tell me about f star of w comma z? You're given that they're separable. Think of them. Just think of them in two dimensions, but they're separable. It's a special case. Think of it f of xy equal to f1 of x plus f2 of y. Simplest. It's always good to have examples running through your mind. So, for example, f of u comma v is simply u plus v. Why does it hurt? So what do you think the conjugate of f star of w f is? I would like to have it as additive. Question is it additive? You just stare at the definition, it should be obvious. What's the definition of f star of w comma z? You take the inner product of wz with uv minus f of uv. F of uv separates, inner product of wz with uv separates, so everything separates. So it's a separate. It's as simple as that. Sometimes the brutal definitions are enough. So what is this? Wz or transpose uv. So far so good. Minus f of uv. Now this is separable. It's a linear. Keeping it for the moment. So over. But this is same as wu minus f of u plus z. And what is the supremizing over? U, right? This one, F1 minus 1. Yes. Now what is this equal to? If everything is separable, the supremum is separable. There is no dependency across. So this is same as supremizing blah over U plus supremizing V over. Exactly. So this is equal to F1 star of W plus F2 star of Z. If they're not separable, then what happens? So f of uv, if they're not separable, then what can you say? We'll take an example if you want. Is there any hope of finding any interesting relationship? When you get stuck, you'll get stuck at this. Get supremum of u comma v w transpose u minus. Now I don't have f1. All I have is f of uv and plus of z transpose v. Any guesses to what will happen?
Unbounded.
Unbounded.
Because
See, what are we interested in? We're trying to find the conjugate in terms of the individual conjugates. Individual conjugates, can I even define individual conjugates now? When it's not separable. It's not a probability distribution function where I can fix one and do something interesting. So there's already a problem. What does it even mean by f1 star and f2 star? You should have objected to what I was asking. How do I even define f1 star? All I'm given is a joint function. For example, if I'm given xy equal to x times y, what does it even mean? Call it f1x and f2y. Fix y equal to 1. Why? There's no such reason. Okay. So let me
Break the FUV to f1 u plus f1 p, and you can just divide the supremum so that you will get for the first term u w transpose.
how do I do that? For example, it's x times y. How do I break it up? Okay, so what did we say? When f is differentiable, what are the optimizing x star? Said something. Gradient of y is equal to now if I give you that so this is I'm going to assume for the moment which I have not proven. We'll prove this in the class. That f is strictly convex or strongly convex. Either of them will work. Strictly convex means the inequality is strict. Strongly convex had some other knowledge. So what, from your earlier knowledge, what do you know about strictly convex functions? That the optimizer is unique. That's all I'm going to use really. We'll prove this. Yes. So using this, what can I say about f star of y or gradient of f star of y? Is there anything I can conclude about these two quantities by the fact that f is strictly convex? Differentiable is given. Okay, why is that?
There is a unique optimizer, then the supremum will be at that point and cannot be
People at that point, why? Why transpose x minus f of x, right? So why should it? Are you saying the optimizer of f is the supremizer of f star? to go in the right direction, all we can say is what is the domain of f star, and that by that we mean where all is it finite. So finish your argument. You're saying something.
Yes.
We'll keep going back to the definition again and again. Right? By definition. What do I know? The fact that f is strictly convex and differentiable. That there is, let's say, some x bar is, if this notation you have not seen, minimum of f of x is the value attained. The point at which it is called argument. Argument of f of x. So let's say x bar is that. We know that x bar is unique. Okay, so what?
Where f of x is minimum.
If this is unique, is this also unique is the question. Why?
So if for minus f of x, it will be the supremum.
Correct.
And y transpose x is the
It's just a shift.
shift.
Okay.
So the at x prime, the supremum will achieve for the x for any.
Tell me what are you saying precisely? Is x bar?
Yeah. So the supremum will achieve exactly x bar.
Why? What do you have? Your y transpose x bar. You're saying minus f of x bar is greater than equal to any other x.
Yes.
Okay. Why is that so? All I know is fx bar is less than equal to, or actually strictly. Let's put it strictly here.
Yeah. So for some x not, if it is not true,
Mhm.
so then for that part,
For which part? So suppose I am at x bar. Okay. Let's say some neighborhood of x bar. Are you going to go down that path? Is that what you're trying to do?
no, I'm trying to give a contradiction. Like
Fine.
this, suppose
You're saying suppose one is false.
yes,
Okay. Then there exists what?
there will be at least one x naught.
If one is false,
Yes.
then there exists an x naught
Such that y transpose x naught
minus f of
x naught
is
greater than equals to y transpose x bar.
okay. So far so good. Now what?
Now,
So,
I
some will
want-
let you use this.
Yeah, so I want to contradict somehow that that x the argument that we get x bar. So I want to contradict that part.
Go ahead.
Yeah, so if x naught,
Mhm.
so if x naught less then if x bar. If x naught is if x bar less than if x naught.
Mhm.
So if I just move fx naught, fx bar to this side and y bar is not to that side.
There is no y bar, man.
No, y transport.
Yeah.
So I'm just taking all y transport to one side and
Fine.
to x one side.
Fine. Go on.
We'll get a y transport x naught minus x bar
Yes. Greater than
greater than
fx naught minus fx bar.
x bar.
Okay. And fx naught is greater than fx bar by definition.
Yes, and that is greater than 0.
Yes. So you got y transpose x naught minus x bar greater than 0. So
So, yes, why don't
Okay, let me leave this as an exercise. So, all you have to prove is that if f of x is a unique minimizer, this has a unique maximizer. It's not difficult to.
So if F is strongly convex, then minus F is strongly concave, and the Y transpose X minus F is strongly concave, which means it should have a unique optimizer.
That gives you directly just by the definition of it, right? In general, I'm asking something more. Supposing f of x is a unique minimizer, does it have a unique maximizer? For strongly convex, you're using some other property, which is slightly stronger. And what about this? That's what you have to prove. So let me leave this. So this is defined everywhere. That means the domain of f star is all of what? Where is it defined? So f star, the domain is Rn itself, and del f star is actually defined, always exists for all y. So these two things, if you can't prove it for strictly convex, at least prove for strongly convex. They're just one line proofs. Okay, so what I want to spend the rest of the time today is looking back at the homework problem number 2 on homework number 1. Is there anybody who's comfortable on this? I haven't checked your solution. But were people comfortable with the question? That's the most important thing.
I don't want to listen to the because I haven't.
Then you can walk out.
Yes, I want to try it.
Yeah, then you can walk out.
Is it fine?
Yeah, perfectly fine.
Means you will not discuss any other thing.
No. Problem everybody remembers? You're given two sets. Let me call it C and let me call it D. You can walk out.
Yeah.
I'm going to come and lift you and throw you out. And what are we given? It actually doesn't hurt to start at one of these points because the first projection will get you to C. So let's suppose x0 itself is on C. What I'm trying to do? Project to get a y0, project to get a y1, project to get an x1, and so that's what we're going. So is there a pictorial proof at hand? Yeah. What's the simplest C and D you could have worked with? Intervals. Let's just think of first the simplest C and D you could have worked with. Possibly two perpendicular lines. What would have happened? So let's call this C, let's call it D. And this is the only point of intersection. Tell me, what would happen? Sorry, you go.
Right after this second step.
So this is some x0.
First step will get it projected to one line.
Yeah.
In the second step it will go.
Okay. Did people see this? This is how people started. Oh, now let's make it slightly more non-trivial. This is my approach typically. If you're seeing something interesting, this is how you start building intuition. Now instead of this, let's make it more angular, where it will not happen in one step. Okay. So let's make it this. Now what will happen? So x0. So now let's erase this as well. And let's say this is my x0. Okay. C is this, D is this. I'll go again down. Now where will I go? I'll go perpendicular to this.
Then again.
So could you build proof for this? Forget about complicated convex objects. Okay, everybody was able to build a proof for this simple case. I've not checked, so I'm just asking. For such a case, were you able to build a proof which did not require anything? Okay,
This was not.
it's not much.
There was a simple case in the no, right?
Did I give anything simpler? What did I ask you?
Directly to the entrance.
Sorry?
In general two sets, there was no spread.
I agree. I'm not saying that I gave you this. But if people there was difficulty, this is what I would have tried. At least build a proof for this, and then I'll build a proof for the general case. So did anybody complete a proof for this is what I'm asking. So this is to also give you the path forward. If there is a problem for which you are unable to solve something, find the simplest non-trivial case and solve that. So perpendicular was a good starting point, but trivial. This is the first non-trivial step where you have to do something, some work to actually show that it converges to the intersection. So if you've not done it, this is how you should proceed. If you get stuck with something very general, come to the least denominator where things are still interesting. Okay. So now let's try to do the proof for the general case. Here. So what is the basic idea? What is going on? Is that clear? What is going on? Why is it converging?
Distance to the
Distance to what?
boundary of the.
Why boundary?
Because you take projections.
Hmm.
So convex, close convex.
Don't use lots of complicated words. Give me the most intuitive thing you see from the picture when you see these projections.
And you have to like take a projection onto a set.
Yes.
Like to go into the interior of the set, you have to cross the boundary.
Again, why interior?
Okay, to go inside the set.
Why do you have to go inside?
I mean, like to go, like, as in like to the distance from X to any point of the set.
So think about, let's say, let me use my notation here. So let's some point X bar belonging to C intersection D. I'm not specifying what point. What is going on with these projections?
So like, if we are projecting onto D, for example, we want to go to C.
Given you a special point, let's for example, which belongs to this intersection. Don't use any complicated word. Give me the simplest explanation to what is going on in the projections. If it was a 10th standard student, what will, if you show him this geometry, what will he say? What's happening to these points with respect to X bar?
Getting closer.
And I have not specified anything interior, exterior. Essentially, what is happening? You look at this intersection, these projections are getting me closer and closer to the intersection. So any point inside, it doesn't matter in the boundary, interior, take this point or whatever point you want. These guys are getting closer and closer to that. If you saw that, it's not very difficult to build a proof. If you didn't see that, that's where the problem is. It doesn't really matter which important point you picked up. The intuition really is that projections are getting you closer and closer to any point on this. For that matter, just take one single convex set. Let's call it E. When I'm taking a projection, what am I doing? So this point goes to this point. Compared to this point and any other point, what is this new point? When is this true?
Could you repeat that compared to?
So take any set E. You're taking a projection. So let's call this X0. Let's call this X1 and let's call Y. Y be any point belonging to E. I'm not specializing it. Could be anywhere. What is the relationship between distance between Y and X0 and Y and X1? When? This is not a.
Yeah.
What do you have to consider about E? If it is convex, this is going to be true. So that's the first thing you should have noticed. That no matter how I'm doing this, with respect to any point, I'm getting closer. And because I'm given these convex sets. And the intersection is convex. So you could just simply throw these guys out, replace the intersection with E. That's what really is going on. Okay. All right. So let's start. So let me erase this here. So let's say I'm projecting this. Look at this hyper. Look at this hyperplane, which is normal to x0 minus y0. So this is the normal. I'm not drawn it very nicely. It will completely separate. So this is my normal, which is x0 minus y0. Is this okay? With the projection, this is what I'm going to get. Okay. So what does it tell me? That this hyperplane is separating, keeping D on one side. That's all I really need. So what will I get? That this hyperplane D will be a subset of this set to the left of this hyperplane. What is that set? Z such that xk minus yk transpose z minus yk is less than equal to 0. So my iterates are x0, y0, x1, y2, and so on. Is this okay? This is essentially the step you need to. There's nothing more actually you need to do. From here onwards, it will be triangle inequalities. Nothing else. And some extraction of some sequences or subsequences. Okay. Fine. Now, what is the distance between xk and x bar? Square distance. I'm going to write in terms of by introducing yks. So xk minus yk plus yk minus x bar. All right. So this will give me xk minus yk whole square plus yk minus x bar whole square and a minus or a plus 2 times xk minus yk transpose yk minus x. Does anybody get the wind? What am I trying to do by doing this? So use that in here. What will I get? Remember, x bar belongs to both C intersection D.
Then because z minus yk times like xk minus yk whole transpose z minus yk less than or equal to 0.
Yeah.
So here we flip that around yk minus x bar. So that thing will be greater than or equal.
Okay.
So then this thing will be greater than or equal to just
The first two terms.
Yeah.
That's all I get, and the proof actually follows. So now you can use, let's call it equation 1. 1 will give you, you don't have to write, it will be there on the video. You can just follow for the moment. I can drop this term and just get the first term. Now what is going on? What is the interpretation of this equation? What has it done?
we have that xk minus x bar the distance.
That's not useful. This is what is useful.
Equal to yk.
So think of this quantity, that yk minus x bar is less than equal to xk minus x bar minus a positive quantity. So what has happened? Wherever xk was, yk has gone closer to x bar compared to xk. And that is the progression I'm making. And if I flip everything around with xk's and yk's, I'll get the same inequality with just xk's and yk's flipped up. Okay. So in individual step, I'm getting closer to x bar. That's essentially what all of this means. So similarly, So implication is yk is closer to x bar than xk. Similar to what we did, because C is also convex as D was. When you're taking the backwards projection, you'll again get another hyperplane and you'll get the same answer. Similar to what we showed. Xk plus 1 minus x bar is less than equal to yk minus x bar minus xk plus 1 minus all this 3 the before is, let's call this. Okay, now what should I do? So far all I've shown is that in each step I'm decreasing the distance. For convergence, what more do I need?
It's also bounded below.
Okay, what sequence is bounded?
It's distance that you have. As in distance of xk to x bar.
Mhm.
And then that sequence, distance of xk to x bar, xk plus 1 to x bar, that sequence is bounded below by 0.
Okay.
The convergent sequence is bounded below. So it must
Mhm.
not just, the sequence that is bounded below, so it must come. So the decreasing sequence that is bounded below by 0, so it must come.
Bounded below.
I mean, the distance is always greater than the sequence.
Okay.
And it's also decreasing sequence.
So before that, don't I have to claim this? And you can essentially from 2 and 3, this will follow. Okay. Now what are you saying?
The sequence that is bounded below by 0.
Yes. So xk and yk or xk minus x bar.
That is
This, right? I can't work with this alone. I have to keep looking at the distance. So xk minus x bar, yk minus x bar are bounded. So I have a limit point. I still don't know if they have a limit. All I know is they have a limit point. Okay. Now what should I do?
it's bounded and it is also decreasing sequence. So then from one
That is somewhat complicated.
should we prove that?
You don't have to prove that, but something will miss from that. You don't even need that. So let's call the limit point to be x star. Okay. I started as my target of x bar, some point which belongs to this intersection. Now I'm saying that these guys are going to x star. Okay. Now what is sufficient to prove what I want to prove? So suppose x star belongs to C intersection D. Am I done?
We want to find the point inside the intersection. X star belongs to that thing.
So I'll have to prove essentially that x star belongs to C intersection D. But when I started, I said any point is fine for, so I can always replace this point with x star. So that much is fine. All I need to do is to show that x star belongs to both C and D. So can you show me first how it belongs to C and then you show me how it belongs to D? That's all is remaining. So we're also given that C and D are not only convex, they're also closed. So what is the property we can use here? So if x star is a limit point of what sequence? So it's definitely inside C. Why is it inside D? Okay. Some few details are missing in this.
If you show that there is a unique limit point.
See, whatever I've done, I've said something which you should have jumped on. I've written two sequences and saying they have the same limit point. I've not proven anything of that sort. So X star is a limit point of one of them. I have to show that the other guy is also going to go there. That's what is remaining to be shown. So let's say the limit point X star is of xk minus x bar. Then I have to show something that X star also belongs to C intersection D. Here I've written as a common point, which need not be true. I don't have like this, that's more difficult. That's unnecessary actually. All you should take is xk minus x bar by definition as a limit point X star. So X star by the closeness of C also belongs to C. So that much better. All we have to show is X star also belongs to D. Okay. So I'll leave that much part as exercise. So bounded. So let xk minus x bar have a limit point X star by closeness of C, that implies X star belongs to C. That much is fine. Okay. So let's write this sequence x0 minus x bar, y0 minus x bar, x1 minus x bar, y1 minus x bar. What kind of sequence is this? We've shown something. Consecutively, they are decreasing. Okay. So this sequence also converges. Not only these, if I look individually at x's, they're converging. Similarly, this interlaced also converge. So now from my 2 and 3, what do I get? Yk minus xk. This is the punchline really. That, sorry, xk plus 1 minus yk must converge to do people see why? What's happening to this sequence? This is converging. And what kind of sequence is this?
It's the difference between.
It's a difference between them. So if this is sequence is converging, the difference sequence better converge to 0. You're not happy?
Really less than difference.
Just converge to 0 is enough. So by definition of X star, subsequence of what was xk minus or the limit point X star. Oh, so definition. So let us say okay, so I need to let xk have a limit point of X. The sequence xk itself has a limit point X star. This everything else is fine. By definition of X star, subsequence of xk converges to that's just by definition of a limit point. So what is the distance of xk comma d? See, xk's are over c's is equal to distance of xk comma yk. Yk is in D, xk is in C. So this distance is equal to or less than equal to, by my projection, it better be equal, right? Because that's a definition. And what is happening to this?
That will go to 0.
This is going to 0. So what can you say about x star belonging to D or not? That's all you really need to do. Xk is going to x star. Distance between xk and yk is going to 0. Yk belongs to D. D is closed. So x star better belong to D. And then eventually you choose x bar equal to x star and finish. You don't need any fancy. All you really need is the hyperplane separation. That's really all you need. And some triangle inequalities. That's all you need the proof. It's a very interesting and nice proof. And I would again look back at this. If you did this, it would have been sufficiently. If you can show this without having to look at all these technical difficulties, that's fine. You don't necessarily have to do the most general proof. But people see, how is it easier here? Why is it easier? What's so special about this special case, which I don't have to do all this?
The distance keeps reducing by a constant factor.
You see the contraction? This is actually that's called contraction. And contraction gives you, so if sequence, what is happening in each sequence, if suppose xk is a sequence which is equal to a power k times, or is a power xk minus 1, where a is less than 1. Can you show that xk converges to 0? That's the simplest sequence. You start with, let's say, xk minus 1 is 1, x0 is 1, sorry, and a is half. This is nothing but the normal 1 half 1 by 2 square, simplest series. And this converges to 0. If you can show this is, if you could have observed this, then you would have gotten an answer for here. You should be able to get an A, which is not necessarily half, but something. So what all you have to say is A is at least so much, and then you're fine. If A also goes to 1, then you have to be slightly careful. So if you show that xk is 1 minus some ak times xk minus 1, where ak is increasing, then you have to be careful. But if ak is, it has some lower bound irrespective of k, then you are just through directly. And somehow that will be readily applicable here. So at least get to the case where you understand what is going on and prove it. You don't necessarily have to go the most general, most difficult, covering all bases. You don't necessarily have to. Okay, let's stop here. And this goes for